Lying just beneath everyday reality is a breathtaking world where much of what we perceive about the universe is wrong. Physicist and best-selling author Brian Greene takes you on a journey that bends the rules of human experience.
Why don't we ever see events unfold in reverse order? According to the laws of physics, this can happen.
It's a world that comes to light as we probe the most extreme realms of the cosmos, from black holes to the Big Bang, to the very heart of matter itself.
I'm gonna have what he's having.
Here, our universe may be one of numerous parallel realities. The three-dimensional world may be just an illusion, and there's no distinction between past, present, and future.
But how could this be? How could we be so wrong about something so familiar?
Does it bother us? Absolutely.
There's no principle built into the laws of nature that say that theoretical physicists have to be happy.
It's a game-changing perspective that opens up a new world of possibilities. Coming up, the realm of tiny atoms and particles, the quantum realm. The laws here seem impossible.
There's a sense in which things don't like to be tied down to just one location.
Yet they're vital to everything in the universe.
There's no disagreement between quantum mechanics and any experiment that's ever been done.
What do they reveal about the nature of reality? Take a quantum leap on the fabric of the cosmos right now on Nova.
Major funding for NOVA is provided by the following: David H. Koch and
Discovering New Knowledge. HHMI.
and by the Corporation for Public Broadcasting, and by contributions to your PBS station from viewers like you. Thank you. Major funding for the fabric of the cosmos is provided by the National Science Foundation, where discoveries begin. And the Alfred P. Sloan Foundation, supporting original research and public understanding of science, technology, engineering, and mathematics. Additional funding is provided by the Arthur Vining Davis Foundations, dedicated to strengthening America's future through education. The U.S. Department of Energy's Office of Science, and the George D. Smith Fund.
For thousands of years, we've been trying to unlock the mysteries of how the universe works. And we've done pretty well, coming up with a set of laws that describes the clear and certain motion of galaxies and stars and planets. But now we know, at a fundamental level, things are a lot more fuzzy, because we've discovered a revolutionary new set of laws that have completely transformed our picture of the universe. From outer space to the heart of New York City to the microscopic realm, our view of the world has shifted thanks to these strange and mysterious laws that are redefining our understanding of reality. They're the laws of quantum mechanics. Quantum mechanics rules over every atom and tiny particle in every piece of matter, in stars and planets, in rocks and buildings, and in you and me. We don't notice the strangeness of quantum mechanics in everyday life, but it's always there if you know where to look. You just have to change your perspective and get down to the tiniest of scales, to the level of atoms and the particles inside them. Down at the quantum level, the laws that govern this tiny realm appear completely different from the familiar laws that govern big, everyday objects. And once you catch a glimpse of them, you never look at the world in quite the same way. It's almost impossible to picture how weird things can get down at the smallest of scales. But what if you could visit a place like this, where the quantum laws were obvious, where people and objects behaved like tiny atoms and particles? You'd be in for quite a show. Here, objects do things that seem crazy. I mean, in the quantum world, there's a sense in which things don't like to be tied down to just one location, or to follow just one path. It's almost as if things were in more than one place at a time. And what I do here can have an immediate effect somewhere else, even if there's no one there. And here's one of the strangest things of all. If people behave like the particles inside the atom, then most of the time, you wouldn't know exactly where they were. Instead, they could be almost anywhere until you look for them. Hey, I'm gonna have what he's having. So why do we believe these bizarre laws? Well, for over 75 years, we've been using them to make predictions for how atoms and particles should behave. And in experiment after experiment, the quantum laws have always been right.
It's the best theory we have.
There are literally billions of pieces of confirming evidence for quantum mechanics.
It has passed so many tests of so many bizarre predictions.
There's no disagreement between quantum mechanics and any experiment that's ever been done.
The quantum laws become most obvious when you get down to tiny scales like atoms. But consider this, I'm made of atoms, so are you. So is everything else we see in the world around us. So it must be the case that these weird quantum laws are not just telling us about small things. They're telling us about reality. So how did we discover them? These strange laws that seem to contradict much of what we thought we knew about the universe. Not long ago, we thought we had it pretty much figured out. The rules that govern how planets orbit the sun, how a ball arcs through the sky, how ripples move across the surface of a pond. These laws were all spelled out in a series of equations called classical mechanics, and they allowed us to predict the behavior of things with certainty. It all seemed to be making perfect sense, until about 100 years ago, when scientists were struggling to explain some unusual properties of light. In particular, the kind of light that glowed from gases when they were heated in a glass tube. When scientists observed this light through a prism, they saw something they'd never expected.
If you heated up some gas and looked at it through a prism, it formed lines. Not the continuous spectrum that you see projected by a piece of cut glass on your table, but very distinct lines.
It wouldn't give out a smeared, kind of complete rainbow of light. It would give out sort of pencil beams of light at very specific colors.
And it was something of a mystery how to understand what was going on.
An explanation for the mysterious lines of color would come from a band of radical scientists who at the beginning of the 20th century were grappling with the fundamental nature of the physical world. And some of the most startling insights came from the mind of Niels Bohr, a physicist who loved to discuss new ideas over ping pong. Bohr was convinced that the solution to the mystery lay at the heart of matter, in the structure of the atom. He thought that atoms resembled tiny solar systems, with even tinier particles called electrons orbiting around a nucleus, much the way the planets orbit around the sun. But Bohr proposed that unlike the solar system, electrons could not move in just any orbit. Instead, only certain orbits were allowed.
And he had a really surprising and completely counter-physical idea, which was that there were definite states, fixed orbits that these electrons could have, and only those orbits.
Bohr said that when an atom was heated, its electrons would become agitated and leap from one fixed orbit to another. Each downward leap would emit energy in the form of light in very specific wavelengths, and that's why atoms produce very specific colors. This is where we get the phrase quantum leap.
If it weren't for the quantum leap, you would have this smear of color coming out from an atom as it got excited or de-excited. But that's not what we see in the laboratory. You see very sharp reds and very sharp greens. It's the quantum leap that's the origin and the author of that sharp color.
What made the quantum leap so surprising was that the electron goes directly from here to there, seemingly without moving through the space in between. It was as if Mars suddenly popped from its own orbit out to Jupiter. Bohr argued that the quantum leap arises from a fundamental and fundamentally weird property of electrons and atoms, that their energy comes in discrete chunks that cannot be subdivided, specific minimum quantities called quanta. And that's why there are only discrete, specific orbits that electrons can occupy.
An electron had to be here or there and simply nowhere in between. And that's like nothing we experience in everyday life.
Think of your daily life. When you eat food, you think your food is quantized? Do you think that you have to take a certain amount of minimum food? Food is not quantized. But the energy of electrons in an atom are quantized. That is very mysterious, why that is.
As mysterious as it might be for tiny particles in an atom to act this way, the evidence quickly mounted showing that Bohr was right. In more and more experiments, electrons followed a different set of rules than planets or ping pong balls. Bohr's discovery was a game changer. And with this new picture of the atom, Bohr and his colleagues found themselves on a collision course with the accepted laws of physics. The quantum leap was just the beginning. Soon Bohr's radical views would bring him head-to-head with one of the greatest physicists in history. Albert Einstein was not afraid of new ideas. But during the 1920s, the world of quantum mechanics began to veer in a direction Einstein did not want to go. A direction that sharply diverged from the absolute definitive predictions that were the hallmark of classical physics.
If you asked Einstein or other physicists at the time what it was that distinguished physics from all kind of flaky speculation, they would have said it's that we can predict things with certainty. And quantum mechanics seemed to pull the rug out from under that.
One test in particular, which would come to be known as the double-slit experiment, exposed quantum mysteries like no other. If you're looking for a description of reality based on certainty, your expectations would be shattered. We can get a pretty good feel for the double-slit experiment and how dramatically it alters our picture of reality by carrying out a similar experiment, not on the scale of tiny particles, but on the scale of more ordinary objects, like those you'd find here in a bowling alley. But first, I need to make a couple of adjustments to the lane. You'd expect that if I roll a few of these balls down the lane, they'll either be stopped by the barrier or pass through one or the other slit and hit the screen at the back. And in fact, that's just what happens. Those balls that make it through always hit the screen directly behind either the left slit or the right slit. The double slit experiment was much like this, except instead of bowling balls, you use electrons, which are billions of times smaller. You can picture them like this. Let's see what happens if I throw a bunch of these balls. When electrons are hurled at the two slits, something very different happens on the other side. Instead of hitting just two areas, the electrons land all over the detector screen, creating a pattern of stripes, including some right between the two slits, the very place you'd think would be blocked. So, what's going on? Well, to physicists, even in the 1920s, this pattern could mean only one thing: waves. Waves do all kinds of interesting things, things that bowling balls would never do. They can split. They can combine. If I sent a wave of water through the double slits, it would split in two, and then the two sets of waves would intersect. Their peaks and valleys would combine, getting bigger in some places, smaller in others, and sometimes they'd cancel each other out. With the height of the water corresponding to brightness on the screen, the peaks and valleys would create a series of stripes and what's known as an interference pattern. So how could electrons, which are particles, form that pattern? How could a single electron end up in places a wave would go?
Particles are particles, waves are waves. How can a particle be a wave? Unless you give up the idea that it's a particle and think, aha, this thing that I thought was a particle was actually a wave.
A wave in an ocean? That's not a particle. The ocean is made out of particles, but the waves in the ocean are not particles. And rocks are not waves. Rocks are rocks. So a rock is an example of a particle, an ocean wave is an example of an ocean wave, and now somebody's telling you a rock is like an ocean wave. What?
Back in the 1920s, when a version of this experiment was first done, scientists struggled to understand this wavy behavior. Some wondered if a single electron, while in motion, might spread out into a wave. And the physicist Erwin Schrödinger came up with an equation that seemed to describe it.
Schrödinger thought that this wave was a description of an extended electron, that somehow an electron got smeared out, and it was no longer a point, but was like a mush.
There was a lot of argument about exactly what this represented.
Finally, a physicist named Max Born came up with a new and revolutionary idea for what the wave equation described. Born said the wave is not a smeared out electron or anything else previously encountered in science. Instead, he declared it's something that's really peculiar, a probability wave. That is, Born argued that the size of the wave at any location predicts the likelihood of the electron being found there.
Where the wave is big, that's not where most of the electron is. That's where the electron is most likely to be.
And that's just very strange, right? So the electron on its own seems to be a jumble of possibilities.
You're not allowed to ask, where is the electron right now? You are allowed to ask, if I look for the electron in this little particular part of space, what is the likelihood I will find it there? I mean, that bugs anyone, anytime.
As weird as it sounds, this new way of describing how particles like electrons move is actually right. When I throw a single electron, I can never predict where it will land. But if I use Schrodinger's equation to find the electron's probability wave, I can predict with great certainty that if I throw enough electrons, then say 33.1% would end up here, 7.9% would end up there, and so on. These kinds of predictions have been confirmed again and again by experiments. And so the equations of quantum mechanics turn out to be amazingly accurate and precise, so long as you can accept that it's all about probability. If you think that probability means you're reduced to guessing, the casinos of Las Vegas are ready to prove you wrong. Try your hand at any one of these games of chance, and you can see the power of probability. Let's say I place a $20 bet on number 29 here at the roulette table. The house doesn't know whether I'll win on this spin, or the next, or the next.
1.
But it does know the probability that I'll win. In this game, it's 1 in 38.
21. 29.
So even though I may win now and then, in the long run, the house always takes in more than it loses. The point is, the house doesn't have to know the outcome of any single card game, roll of the dice, or spin of the roulette wheel. Casinos can still be confident that over the course of thousands of spins, deals, and rolls, they will win. And they can predict with exquisite accuracy exactly how often. According to quantum mechanics, the world itself is a game of chance much like this. All the matter in the universe is made of atoms and subatomic particles that are ruled by probability, not certainty.
At base, nature is described by an inherently probabilistic theory. And that is highly counterintuitive and something which many people would find difficulty accepting.
One person who found it difficult was Einstein. Einstein could not believe that the fundamental nature of reality at the deepest level was determined by chance.
And this is what Einstein could not accept. Einstein said, God does not throw dice. He didn't like the idea that we couldn't with certainty say this happens or that happens.
But a lot of other physicists weren't so put off by probability, because the equations of quantum mechanics gave them the power to predict the behavior of groups of atoms and tiny particles with astounding precision. Before long, that power would lead to some very big inventions. Lasers, transistors, the integrated circuit, the entire field of electronics.
If quantum mechanics suddenly went on strike, every single machine that we have in the US almost would stop functioning.
The equations of quantum mechanics would help engineers design microscopic switches that direct the flow of tiny electrons and control virtually every one of today's computers, digital cameras, and telephones.
All the devices that we live on, diodes, transistors, just to form the basis of information technology, the basis of daily life in all sorts of ways. They work, and why do they work? They work because of quantum mechanics.
I'm tempted to say that without quantum mechanics, we'd be back in the dark ages. I guess more accurately, without quantum mechanics, we'd be back in the 19th century. Steam engines, telegraph signals.
Quantum mechanics is the most successful theory that we physicists have ever discovered. And yet we're still arguing about what it means, what it tells us about the nature of reality.
In spite of all its triumphs, quantum mechanics remains deeply mysterious. It makes all this stuff run, but we still haven't answered basic questions raised by Albert Einstein all the way back in the 1920s and 30s. Questions involving probability and measurement, the act of observation. For Niels Bohr, measurement changes everything. He believed that before you measured or observed a particle, its characteristics were uncertain. For example, an electron in the double-slit experiment. Before the detector at the back pinpoints its location, it could be almost anywhere with a whole range of possibilities, until the moment you observe it. And only at that point will the location's uncertainty disappear. According to Bohr's approach to quantum mechanics, when you measure a particle, the act of measurement forces the particle to relinquish all of the possible places it could have been and select one definite location where you find it. The act of measurement is what forces the particle to make that choice. Niels Bohr accepted that the nature of reality was inherently fuzzy, but not Einstein. He believed in certainty, not just when something is measured or looked at, but all the time. As Einstein said, I like to think the moon is there, even when I'm not looking at it.
That's what Einstein was so upset about. Do we really think the reality of the universe rests on whether or not we happen to open our eyes? That's just bizarre.
Einstein was convinced something was missing from quantum theory, something that would describe all the detailed features of particles, like their locations, even when you were not looking at them. But at the time, few physicists shared his concern.
And Einstein just thought it was giving up on the job of the physicist. It wasn't bad physics per se, it just was totally incomplete.
That's Einstein's refrain. Quantum mechanics is not incorrect, it's insofar as it goes, but it's incomplete. It doesn't capture all of the things that can be said or predicted with certainty.
Despite Einstein's arguments, Niels Bohr remained unmoved. When Einstein repeated that God does not play dice, Bohr responded, "Stop telling God what to do." But in 1935, Einstein thought he'd finally found the Achilles heel of quantum mechanics. Something so strange, so counter to all logical views of the universe, he thought it held the key to proving the theory was incomplete. It's called entanglement.
The most bizarre, the most absurd, the most crazy, the most ridiculous prediction that quantum mechanics makes is entanglement.
Entanglement is a theoretical prediction that comes from the equations of quantum mechanics. Two particles can become entangled if they're close together and their properties become linked. Remarkably, quantum mechanics says that even if you separated those particles, sending them in opposite directions, they could remain entangled, inextricably connected. To understand how profoundly weird this is, consider a property of electrons called spin. Unlike a spinning top, an electron spin, as with other quantum qualities, is generally completely fuzzy and uncertain until the moment you measure it. And when you do, you'll find it's either spinning clockwise or counterclockwise. It's kind of like this wheel. When it stops turning, it will randomly land on either red or blue. Now imagine a second wheel. If these two wheels behave like two entangled electrons, then every time one landed red, the other is guaranteed to land on blue. And vice versa. Now, since the wheels are not connected, that's suspicious enough. But the quantum mechanics embraced by Niels Bohr and his colleagues went even further, predicting that if one of the pair were far away, even on the moon, with no wires or transmitters connecting them, still, if you look at one and find red, the other is sure to be blue. In other words, if you measured a particle here, not only would you affect it, but your measurement would also affect its entangled partner, no matter how distant. For Einstein, that kind of weird long-range connection between spinning wheels or particles was so ludicrous, he called it spooky. Spooky action at a distance.
What's surprising is that when you make a measurement of one particle, you affect the state of the other particle. You change its state.
There's no forces or pulleys or, telephone wires. There's nothing connecting those things, right? How could my choice to act here have anything to do with what happens over there?
So there's no way they can communicate with each other. So it is completely bizarre.
Einstein just could not accept that entanglement worked this way, convincing himself that only the math was weird, not reality. He agreed that entangled particles could exist, but he thought that there was a simpler explanation for why they were linked that did not involve a mysterious long-distance connection. Instead, he insisted that entangled particles were more like a pair of gloves. Imagine someone separates the two gloves, putting each in a case. Then that person delivers one of those cases to me and sends the other case to Antarctica. Thanks. Before I look inside my case, I know that it has either a left hand or a right hand glove. And when I open my case, if I find a left hand glove, then at that instant, I know the case in Antarctica must contain a right-hand glove, even though no one has looked inside. There's nothing mysterious about this. Obviously, by looking inside the case, I've not affected either glove. This case has always had a left-hand glove, and the one in Antarctica has always had a right-hand glove. That was set from the moment the gloves were separated and packed away. Now, Einstein thought that exactly the same idea applies to entangled particles. Whatever configuration the electrons are in must have been fully determined from the moment that they flew apart. So, who was right? Bohr, who championed the equations that said that particles were like spinning wheels that could immediately link their random results even across great distances, or Einstein, who believed there was no spooky connection, but instead, everything was decided well before you looked. Well, the big challenge in figuring out who is right, Bohr or Einstein, is that Einstein is saying a particle, say, has a definite spin before you measure it. How do you check that, you say to Einstein? He says, well, measure it, and you'll find the definite spin. Bohr would say, but it's the act of measurement that brought that spin to a definite state. No one knew how to resolve the problem. So the whole question came to be considered philosophy, not science. In 1955, Einstein died, still convinced that quantum mechanics offered, at best, an incomplete picture of reality. In 1967, at Columbia University, Einstein's mission to challenge quantum mechanics was taken up by an unlikely recruit. John Clauser was on the verge of earning a PhD in astrophysics. The only thing standing in his way was his grade in quantum mechanics.
When I was still a graduate student, try as I might, I could not understand quantum mechanics.
Clauser was wondering if Einstein might be right when he made a life-altering discovery. It was an obscure paper by a little-known Irish physicist named John Bell. Amazingly, Bell seemed to have found a way to break the deadlock between Einstein and Bohr and show once and for all who was right about the universe.
I was convinced that the quantum mechanical view was probably wrong.
Reading the paper, Clauser saw that Bell had discovered how to tell if entangled particles were really communicating through spooky action, like matching spinning wheels, or if there was nothing spooky at all, and the particles were already set in their ways, like a pair of gloves. What's more, With some clever mathematics, Bell showed that if spooky action were not at work, then quantum mechanics wasn't merely incomplete, as Einstein thought. It was wrong.
I came to the conclusion that, my God, this is one of the most profound results I've ever seen.
Bell was a theorist, but his paper showed that the question could be decided if you could build a machine that created and compared many pairs of entangled particles.
Bell turned the question into an experimental question.
It wasn't just going to be about philosophy or trading pieces of paper.
And the experiment that he envisioned could be done.
You could really set up an actual experiment to force the issue.
Clauser set about constructing a machine that would finally settle the debate.
Now, I was just this punk graduate student at the time. This really seemed like, wow. There's always the slim chance that you will find a result that will shake the world.
Clauser's machine could measure thousands of pairs of entangled particles and compare their spins in many different directions. As the results started coming in, Clauser was surprised and not happy.
I kept asking myself, what have I done wrong? What mistakes have I made in this?
Clauser repeated his experiments, and soon French physicist Alain Aspect developed a more sophisticated test. With significantly more definitive results, Aspect removed virtually all lingering doubt. Clauser's and Aspect's results are truly shocking. They prove that the math of quantum mechanics is right. Entanglement is real. Quantum particles can be linked across space. Measuring one thing can in fact instantly affect its distant partner, as if the space between them didn't even exist. The one thing that Einstein thought was impossible, spooky action at a distance, actually happens.
I was, again, very saddened that I had not overthrown quantum mechanics, because I still had, and to this day, still have great difficulty in understanding it.
That is the most bizarre thing of quantum mechanics. It is impossible to even comprehend. Don't even ask me why. Don't ask me which you're going to, how it works, because it's an illegal question. All we can say is that is apparently the way the world ticks.
So if we accept that the world really does tick in this bizarre way, could we ever harness the long-distance spooky action of entanglement to do something useful? Well, one dream has been to somehow transport people and things from one place to another without crossing the space in between. In other words, teleportation.
Lead me aboard. Energize. Energize.
Star Trek has always made beaming or teleporting look pretty convenient. It seems like pure science fiction, but could entanglement make it possible? Remarkably, tests are already underway here on the Canary Islands off the coast of Africa.
We do the experiments here on the Canary Islands because you have 2 observatories, and after all, it's a nice environment.
Anton Zeilinger is a long way from teleporting himself or any other human. But he is trying to use quantum entanglement to teleport tiny individual particles. In this case, photons, particles of light. He starts by generating a pair of entangled photons in a lab on the island of La Palma. One entangled photon stays on La Palma, while the other is sent by laser to the island of Tenerife, 89 miles away. Now Zeilinger brings in a third photon, the one he wants to teleport, and has it interact with the entangled photon on La Palma. the team studies the interaction, comparing the quantum states of the two particles. And here's the amazing part. Because of spooky action, the team's able to use that comparison to transform the entangled photon on the distant island into an identical copy of that third photon. It's as if the third photon has teleported across the sea without traversing the space between the islands.
Sort of extract the information carried by the original and make a new original there.
Using this technique, Zeilinger has successfully teleported dozens of particles. But could this go even further? Since we're made of particles, could this process make human teleportation possible one day?
Welcome to New York City.
Let's say I want to get to Paris for a quick lunch. Well, in theory, entanglement might someday make that possible. Here's what I'd need. A chamber of particles here in New York that's entangled with another chamber of particles in Paris.
Right this way, Mr. Green.
I would step into a pod that acts sort of like a scanner or a fax machine. While the device scans the huge number of particles in my body, more particles than there are stars in the observable universe, it's jointly scanning the particles in the other chamber, and it creates a list that compares the quantum state of the two sets of particles. And here's where entanglement comes in. Because of spooky action at a distance, that list also reveals how the original state of my particles is related to the state of the particles in Paris. Next, the operator sends that list to Paris. There, they use the data to reconstruct the exact quantum state of every single one of my particles. And a new me materializes. It's not that the particles traveled from New York to Paris. It's that entanglement allows my quantum state to be extracted in New York and reconstituted in Paris, down to the last particle.
Bonjour, Monsieur Green.
Hi there. So, here I am in Paris, an exact replica of myself. And I'd better be, because measuring the quantum state of all my particles in New York has destroyed the original me.
It is absolutely required in the quantum teleportation protocol that the thing that is teleported is destroyed in the process. And, you know, that does make you a little anxious. I guess you would just end up being a lump of neutrons, protons, and electrons. You wouldn't look too good.
Now, we are a long way from human teleportation today, but the possibility raises a question. Is the Brian Greene who arrives in Paris really me? Well, there should be no difference between the old me in New York and the new me here in Paris. And the reason is that, according to quantum mechanics, it's not the physical particles that make me me. It's the information those particles contain. And that information has been teleported exactly for all the trillions of particles that make up my body.
It is a very deep philosophical question whether what arrives at the receiving station is the original or not. My position is that by original we mean something which has all the properties of the original. And if this is the case, then it is the original.
I wouldn't step into that machine.
Whether or not human teleportation ever becomes a reality, the fuzzy uncertainty of quantum mechanics has all sorts of other potential applications. Here at MIT, Seth Lloyd is one of many researchers trying to harness quantum mechanics in powerful new ways.
Quantum mechanics is weird. That's just the way it is. So, you know, life is dealing us weird lemons. Can we make some weird lemonade from this?
Lloyd's weird lemonade comes in the form of a quantum computer.
These are the guts of a quantum computer.
This gold and brass contraption might not look anything like your familiar laptop, but at its heart, it speaks the same language, binary code, a computer language spelled out in zeros and ones, called bits.
So the smallest chunk of information is a bit. And what a computer does is simply busts up the information to the smallest chunks and then flips them really, really, really rapidly.
This quantum computer speaks in bits, but unlike a conventional bit, which at any moment can be either 0 or 1, a quantum bit is much more flexible.
You know, something here can be a bit. Here is 0, there is 1. That's a bit of information. So if you can have something that's here and there at the same time, then you have a quantum bit or qubit.
Just as an electron can be a fuzzy mixture of spinning clockwise and counterclockwise, a quantum bit can be a fuzzy mixture of being a 0 and a 1. And so a qubit can multitask.
Then it means you can do computations in ways that our classical brains could not have dreamed of.
In theory, quantum bits could be made from anything that acts in a quantum way, like an electron or an atom. The qubits at the heart of this computer are tiny superconducting circuits built with nanotechnology that can run in 2 directions at once. Since quantum bits are so good at multitasking, if we can figure out how to get qubits to work together to solve problems, our computing power could explode exponentially. To get a feel for why a quantum computer would be so powerful, imagine being trapped in the middle of a hedge maze. What you'd want is to find the way out as fast as possible. The problem is there are so many options. And I just have to try them out, one at a time. That means I'm going to hit lots of dead ends, go down lots of blind alleys, and make lots of wrong turns before I finally get lucky and find the exit. And that's pretty much how today's computers solve problems. Though they do it very quickly, they only carry out one task at a time, just like I can only investigate one path at a time in the maze. But if I could try all the possibilities at once, it would be a different story. And that's kind of how quantum computing works. Since particles can, in a sense, be in many places at once, the computer could investigate a huge number of paths or solutions at the same time and find the correct one in a snap. Now, a maze like this only has a limited number of routes to explore, so a conventional computer could find the way out pretty quickly. But imagine a problem with millions or billions of variables, like predicting the weather far in advance. We might be able to forecast natural disasters like earthquakes or tornadoes. Solving that kind of problem right now would be impossible because it would take a ridiculously huge computer. But a quantum computer could get the job done with just a few hundred atoms. And so the brain of that computer, it would be smaller than a grain of sand. There's no doubt we're getting better and better at harnessing the power of the quantum world. And who knows where that could take us. But we can't forget that at the heart of this theory, which has given us so much, there is still a gaping hole. All the weirdness down at the quantum level, at the scale of atoms and particles, where does the weirdness go? Why can things in the quantum world hover in a state of uncertainty, seemingly being partly here and partly there, with so many possibilities, while you and I, who after all are made of atoms and particles, seem to always be stuck in a single, definite state? We are always either here or there. Niels Bohr offered no real explanation for why all the weird fuzziness of the quantum world seems to vanish as things increase in size. As powerful and accurate as quantum mechanics has proven to be, scientists are still struggling to figure this out. Some believe that there's some detail missing in the equations of quantum mechanics. And so, even though there are multiple possibilities in the tiny world, the missing details would adjust the numbers on our way up from atoms to objects in the big world so that it would become clear that all but one of those possibilities disappear, resulting in a single certain outcome. Other physicists believe that all of the possibilities that exist in the quantum world, they never do go away. Instead, each and every possible outcome actually happens. Only most of them happen in other universes, parallel to our own. It's a mind-blowing idea, but reality could go beyond the one universe we all see and be constantly branching off, creating new, alternative worlds where every possibility gets played out. This is the frontier of quantum mechanics, and no one knows where it will lead.
The very fact that our reality is much grander than we thought, much more strange and mysterious than we thought, is to me also very beautiful and awe-inspiring.
The beauty of science is that it allows you to learn things which go beyond your wildest dreams. And quantum mechanics is the epitome of that.
After you learn quantum mechanics, you're never really the same again.
As strange as quantum mechanics may be, what's now clear is that there's no boundary between the worlds of the tiny and the big. Instead, these laws apply everywhere, and it's just that their weird features are most apparent when things are small. And so the discovery of quantum mechanics has revealed a reality, our reality, that's both shocking and thrilling, bringing us that much closer to fully understanding the fabric of the cosmos.
Major funding for NOVA is provided by David H. Koch and
Discovering New Knowledge. HHMI.
and by the Corporation for Public Broadcasting, and by contributions to your PBS station from viewers like you. Thank you. Major funding for the fabric of the cosmos is provided by the National Science Foundation, where discoveries begin. And the Alfred P. Sloan Foundation, supporting original research and public understanding of science, technology, engineering, and mathematics. Additional funding is provided by the Arthur Vining Davis Foundations, dedicated to strengthening America's future through education. The U.S. Department of Energy's Office of Science, and the George D. Smith Fund.